Let's go through this example kind of quickly. The first rational function. So we've got three different rational functions here. Let's look at R1. It's 4x divided by x cubed minus 7. So from your days in algebra, you know that you need, for long-term behavior of rational functions, to compare the degrees, right? You've got a degree 1 sitting on top of a degree 3 polynomial. So it's heavier on bottom than it is on top. The bottom is going to grow a lot faster than the top does. Let's show this with limits. If I look at the limit as x gets larger and larger of 4x over x cubed minus 7, we'll do the same trick that we did with polynomials, and we'll factor out the most powerful term from both numerator and denominator. I get a 4x times a 1 in my numerator. I get an x squared times a 1 minus 7 over x squared in my denominator. Right, if I pull an x squared away from x squared in minus 7. All right, so what happens here? As x gets larger and larger, 1 obviously just stays the same as 1. This parentheses here, 1 minus 7 over x squared, as x gets larger and larger, this 7 over x squared term is going to drop down to 0. So the parentheses approaches the value of 1. So this function for large x values looks like 4x over x squared. Your x's can cancel. You're left with 4 over x. And what happens to 4 over x as x gets larger and larger? Drops down to 0. So we see that from the graph. As x gets larger and larger, our y values drop down to 0. You can also approach minus infinity, and for the same reason, the limit is 0. Right, so that's why you have a horizontal asymptote at 0 when your degree of the denominator is larger than the degree of the numerator. Let's see. Oh, I don't know why these are labeled strangely. Let's look at the third rational function. X cubed divided by x cubed minus 7. So if you remember from algebra, if it's same degree, we have a degree 3 on top of a degree 3. So they're equally as powerful. So they're kind of going to go, they're going to match pretty well. They're going to grow at the same rate. So this is going to approach the horizontal asymptote of the ratio of the leading coefficients. So 1 over 1. Let's see why that is. Limit as x gets larger and larger, x cubed over x cubed minus 7. We'll do the exact same trick and pull out the most powerful term from numerator and denominator. And for all the same reasons, as x gets larger and larger, this parentheses approaches the value of 1. So this function is really just x cubed over x cubed, which is just 1. So that's why we have a horizontal asymptote at the y value of 1 as x gets larger and larger. Right, you can see that if there was a 3 in front of that x cubed, then it would give you a 3, right? But it's the ratio of the leading coefficients because our polynomials in our numerator and denominator are of the same degree. All right, R2, our third rational function. Here we have the case where we have a 5th degree on top of a 3rd degree, so it's more powerful on top than it is on bottom. So we're going to get polynomial-like behavior. In fact, if you take a degree 5 and divide it by a degree 3, you get a degree 2, right? Because 5 minus 3 is equal to 2. So we're expecting quadratic behavior, which is kind of what you see there, right? This kind of looks like x squared. All right, but let's show that we don't actually have a horizontal asymptote here. We actually do get polynomial-like behavior. Limit as x approaches positive infinity of 4x to the 5th over 40 x cubed minus 7. we'll do the exact same thing. And we'll pull out the most powerful term. I'm going to pull out the x cubed. So this is going to be 40x cubed times 1 minus 7 over x cubed. And for all the same reasons, that parentheses, as x gets larger and larger, drops down to 1. So this function for large values of x looks like 4x to the 5th over 40x cubed. Our x's can cancel, and you're left with 1/10 x squared. Right? We knew it was going to be x squared because it was 5th degree divided by 3rd degree. And that's our end behavior. It looks like x squared, or I guess technically it looks like 1/10 x squared.